cloud is not on the plane. So it's pretty much bent, because this part seems to be about the same distance, but then it drifts to about 470 parsecs. So that part here is bent, and this part is further away from us than the head of the cloud. Let me go back now to what I was telling you about. This is the cluster that we had a little fight about. This is the Orion Nebula, ONC, trapezium cluster right there. This is where we study disks, and how disks become planets. And this is a very important region for star formation. But then there was this guy here that we thought is very strange, because there's no extinction. And that's an O9. How does the O9 don't have his own nebula around it? And we suggested, well, it's in front, there's no extinction. Then a group from here, actually, using Chandra, proved that there has to be the extinction. Column of hydrogen is so low that it cannot be close to the cloud. They actually suggest 50 parsecs, if I believe, if I'm correct, in front of the cloud. And this tells you a bit about the problem of benchmarks. If you wrote your own life that there is an age gradient or an age spread, because you take this as part of the product of this event, then you have a hard time accepting that maybe that's wrong. And what we prove now, or I will not have time to go very deeply into this, is indeed this thing, these blue stars, all B stars here, together with these ones all over the place, they are a layer in front of the cloud. And they're not very, very far. They're 15 parsecs, 20 parsecs in front of the cloud. And not surprisingly then, that the class 2s and the class 3s, which is just formed in the cloud, are also closer. So there's an age gradient, well-defined age gradient, from 0, which stars are forming there, to 5 million years, which are all the blue stars here. And then, as I'll show you later, even closer. Remember the supergiants? We'll talk about the supergiants later. Okay, but maybe it's because, it's an optical telescope. How do you know there's no stars on the other side? Maybe that's you just being fooled. So what we did, we took a sample of stars that we know are young stars and are part of the star formation, the star forming region, and then we plot the distance here. And then you find out that they're all in the front. There's barely anything on the back. We also find out there's something at 100 parsecs of young stars. Also in X-rays, as I'll show you later. This is totally new. I don't know what that is. So, but now just take a sample without the extinctions. Just go for the very low column densities lines of sight, and the same thing happens. They're all between us and the cloud. In other words, there's no young stars on the other side of Orion. There's a really well-defined gradient. So the cloud is shooting stars in one direction only. Unfortunately for us, it's towards us. And we get confused because we have several populations in different layers from about 200 parsecs, I would say, where the supergiants are, Betelgeuse, Rigel, and all those, that after becoming, I think, from the same star formation event. Here we have the Chandra X-ray class trees, and again they're all in the front. They kind of go back, but the same thing with the class 2s. The cloud bends. That part is further away than this part. But then you also have an interesting population of X-ray sources that we thought were class 3s, as close as 100 parsecs, just like the other plot. So I think there's little pieces of evidence that will need to be double-checked, that there is really a continuous of ages from 400 parsecs down to about the distance where supergiants are, which is about 250 parsecs. So, and I think this is really the event, the star formation event in Orion. What we're seeing when you look at ONC, it's just T0. It's just what's happening now. So, what I've just said in pictures, somehow we have Orion 140 parsecs below the plane. In our line of sight, you have, of course, the trapezium, the stuff inside the cloud, but you have this layer of 1980, but then there's other ones that I didn't talk about, and then the supergiants. And this is one beautiful age gradient. And I think this is then how Orion works, and I will... there's also Orion Nebula superbubble, for anyone who knows what that is, and it nicely fits a model where you have distribution of about 200 parsecs of B stars and young stars. Several supernovae took place over the last 20 million years, and they keep powering this Orion Nebula superbubble. It's a nice animation. Take all the, well, not all, but the Parker stars in this case, and let's just shake them so you have a feeling. So the big ones are closer to us, the little ones are further away. And you have this feeling that you're really looking down a tunnel or stream of young stars that I think are coming from the same event. Now, the gas that's there did not form the stars. That gas is gone. But I think there is a hotspot. So you have some, and this is where context matters. If you want to understand how Orion works, that you must have a way, the galaxy must have a way to pile gas at about 400 parsecs that gives you then this stream of young stars with a beautiful age gradient. I don't have time to talk about this, but another reason why we want Gaia a lot is that we don't know the distances very well to these stars, and I think the ISM, the local ISM, is reacting to stars like Sigma SCO. This is Ophiuchus. This is, you might recognize the constellation of Scorpius here. Half of it, then the other part is missing. And all of these are B stars. And all of these are part of upper SCO, one of the regions I showed in SCO-SAN. And in red and blue, you have Planck data, and it's basically mapped to blue being warm dust and red being cold dust. And you see that, you know, there's this cavity where all the B stars, where the center of upper SCO is. But then there's an interesting star there, Sigma, which think we have very strong evidence that it's actually forming these filaments. So, you know, there's a lot of talk about filaments, a lot of talk about, so as we mentioned before, by the way, the cores are these little things. These are the cores that, if you count them all, look like the IMF but shifted. These are the little blobs you see there. And so I guess what I'm trying to say is that you cannot remove the stars. If you want to understand really star formation in the local ISM, you have to have the stars. You have to know what the stars are doing. Because the stars might have been actually building streamers. By the way, that's the name they are known by. And you know, a lot of instabilities. So the picture that I have in mind is much more one of hydrodynamics than anything else. You have a fluid that's been pushed and creates these long striations, these long filaments. And inside them, there's periodic cores that eventually will form stars. All star formation at the moment happens only at the tip of this. This is a little cluster forming there, a little star there, a little star there, nothing there, nothing there. They're just being compressed at the head. You have a long comet. It's exactly like a high-velocity cloud plunging into the galaxy, except that it's the reverse. You have gas that's been pushed by the winds of Sigma SCO in this case. This will be a totally different talk, but it is important to know where the stars are. Finally, a view of the local neighborhood. So now you know there's SCO-SAN, and you can get an IMF in 5 minutes if you want. This part does not belong to, so this 4, we believe, came from the same event, more or less where the sun is now in the galaxy, by the way. Of course, the sun was not there. It was 15 million years ago. These two come also together. This is what I was talking about. This is the stream from Orion projected on itself. So that's why you're seeing one from on the side. You see this one, you're just looking down a long cylinder of stars. And then you have this Mickey Mouse appearance, but it's because there's other interesting groups of stars, by the way, that were not put together, like Taurian and Monorian. Finally, how do you get to Orion? Okay, so I argue that we need to know a lot about the gas, if you want to understand the galaxy, and we want to know really how stars are formed. It seems to me that there's 2 main events in the local neighborhood. That's Orion. Another one is SCO-SAN. SCO-SAN took place 15 million years ago, apparently from something like this, as big as Orion. That was located more or less where the sun is at the moment. But that's gone. That's all gone. The other one is Orion, and that's about 400 parsecs away, and it looks like this. And I argue that there's nothing behind it. All it's happening in front of it. All the population of stars are going this way. So how do you form Orions? And this is where context makes a big difference. So here's the sun. This is from Mark Reed. So this is 2014. The new data, this is even more impressive. The local arm, which is the blue points, go all the way here. And an amazing result is that the local arm is as important as Sagittarius or Perseus. And this is all coming from VLBI work. Orion is that little dot, the blue dot there, and that's the sun. So I think the only, or the easiest explanation that you can find for where Orion is coming from, how do you get to accumulate almost 1 million solar masses? Well, that's the local arm. And here's a simulation by a PhD student from St. Andrews, where you have a shock, a spiral shock, gas going through a spiral shock, where you have the shock is somewhere here, and you have this interesting, again, head-tail structure, perhaps somehow reminding you of a lot of the structure that we see here, or not. But this, I think, is going to be critical for us to understand local star formation. This gives you a nice explanation why you have, how can you accumulate 10 to the 6 solar masses, and how do you stream it in one direction? Well, that's because the gas was already moving that direction. It gets compressed by the shock, it turns into stars, and then streams out of the spiral arm. There's a couple of things that don't add up in this story, and one of them is the age gradient is reversed to what would you expect for a trailing arm. That does make sense. So trail arms should have the gradient ahead of the arm. And if this is the case for the local arm, it's reversed. It should be on that side, not on this side. Well, it could be that, well, this is wrong, the idea. There's a possibility. Or that these are more transient features. And they could be just moving. And the local arm could be moving through the plane and leaving a trail of star formation behind. But this is really the things that I'm very excited about, and I plan to dedicate a lot of time over the next year. And I think we're going to learn a lot about Gaia from, a lot about star formation from Gaia. This is all great if you want to do this, but we don't have the space motion of the gas. We know the space motion. I showed all these movies about the stars. How are you going to do space motion? Gas, you know radial velocity very well. Since the 70s and before, you have terrible measurements of proper motions of gas. How do you do that? So we have a program, a large program at ESO, where we're going to do just that. We're going to measure space motions of the nearby complexes up to 500 parsecs. And we're going to do that by using the YSOs, so you cannot really measure. Well, you could imagine waiting and doing an extinction map 10 years apart. You might see a hint that the map, that the distinctions move in some coherent way. Then you get to know the proper motion. We know now the proper motion of Orion A. I show you 2,000 YSOs. They move in one direction. So we have the space motion for that one. What we're going to do with ESO in the very large 1 degree by 1.5 degree VIRCAM, the VISTA telescope, a survey telescope, we're going to do over 3 years. Every 6 months, we're going to observe all the complexes you can observe from the south. And then we're going to derive proper motions of all these YSOs inside the cloud. We're going to tie them to Gaia, and then you get the 6D with the radial velocity from radio astronomy. We're going to do all, of course, the bread and butter of star formation, but I think I'm very, very excited about space motion of gas, because we really figuring out where, how do you pile up gas, how do you construct molecular clouds, how do they dissolve, and what's the connection between all of them in a local neighborhood. We are expecting to do very accurate 3D maps of these complexes with errors of 5% from the distance, thickness errors of 5 parsecs, 1 parsec, an inclination that, like I showed you before, of 2 parsecs at the extreme of ends of the clouds when you combine Gaia and this data. By the way, this is the Orion Nebula. This is Orion A observed on a pilot project for visions. with the same telescope. This is what we'll get. We get a lot of, this is a visual album of what class 1s look like. There's 5 in Gaia. There's 2,000 of this in Gaia, just on that cloud. So what I showed, the red dots before I showed it on the plot, are these guys here. And you can see they have lots of cavities. And this is important because it's subarc second. This will be very important for YSO characterization and other important science cases. These are the clouds we're going to observe. Here's Vista. And every 6 months, we have all of them observed. It's very large areas. And then we had to develop, and this is my last slide, we had to develop our own software to reduce this data because what comes out of the pipeline was not gentle on the resolution. So we get a gain of resolution of about 20%, which is fundamental if you want to do all kinds of work with of course, characterizing YSOs, but also proper motions. And this is work done in Vienna. So I want to conclude now. And I think it's fair to say that Gaia DR2 is a transforming and rare event in the life of an astronomer. I'm not an astrometrist, and I just did all this astrometry because these 450 people in Europe spent 10 years preparing for this and giving us an absolutely amazing data set. Anyone can get it, including you. Anyone can download the data. Again, you have to wait for it, but it comes. So Gaia in the local neighborhood will give resolved studies of star formation a critical missing link. And this is us trying to argue. We will stop being, very narrow focused on tiny little parts of the cloud that has a cluster and suddenly realizing that this is part of a much larger context. And in fact, star formation is not just what happens in the cloud. There's this distribution in front of the cloud that's not isotropic. So stars do not form isotropically around molecular clouds. They stream out of their cradles, barely expanding. I didn't have time to talk about that, but we have no evidence. It's very hard to measure expansion, which is funny because this is how we discovered them in the first place. They were thought they would be expanding. But no, they're streaming. They're expanding at percent level compared to the stream velocity. Which means that we're going to be able to see lots of streams. They will go on and on the disk for a long time. And you probably can recover them with this 6D data. Several implications for cloud formation process, of course. I mean, if you only form stars towards one direction, in particular the big events, which is Orion. The little events are a bit different. I think they're more the second act. So you have the big event, and they have pieces of gas that then get formed and stretched by the winds and feedback of young stars. But I think we have a good shot of understanding how you get to form giant molecular clouds, in particular if you have their space motion, which is, I think, critical. 3D matters, and the star formation basic observables that we've been using for a long time will probably need to be revised. In a few years, with Gaia and Visions, we'll have an accurate 6D map of a local star-forming YSM, and this is really what drives me here for the sabbatical, and very, very happy about it. And this is just day 5. There's DR2 to come, there's DR4 to come, DR3 to come, DR4 to come. And I thank you very much for your time.
Thank you, Joao. So, I'm sure that Igor,
yeah, I have a question on this, maybe a naive question about the inconsistency between this, the color magnitude diagram and model predictions from the beginning of your talk. This is a pretty young star forming region, right? Yes. It's like 8 million years.
15.
But,
who knows?
But you know, there's very red stars. They take really a while to form, like 30 million years. Maybe they're just pre-main sequence.
They
haven't yet just
so what I showed, that they're all pre-main sequence.
Yeah, so they haven't settled yet. So do these models include those effects from pre-main sequence?
I think this person behind this dude. Are you Charlie?
No.
No. Okay. They do. And it's obviously needs improvement.
With regard to the IMF data, which was fascinating, for a non-Gaia expert, can you explain how you how you distinguish, or maybe you don't, spectroscopic binaries. You know, you look at one star when it's really two, but
Right.
too close.
Right. So there is a filter at the moment in the R2. If there's a suspicion that the star is a binary, it's not in the R2. There are binaries here. You can see the sequence. Maybe here, better even. Not really on this one, but you can see the binary. Oops. The binary sequence here. When it's again, this is not the perfect example. I showed the Pleiades, where you have this really amazing 0.75 separation between the two. But there is no other, at the moment, unless you have radio losses from the ground, there is no other filter. This, by the way, has no filter. There's no optimization of anything except selecting them here, which you probably don't even have to because they separate naturally.
Can you say something about the fraction of binaries?
Not
What's
yet.
inferred?
No, I don't. No. 5 days.
Day 6, maybe.
One flying, so. I mean, yeah, this is an obvious thing to do. I think also interesting would be to figure out why are they all equal mass binaries. I was expecting this to be no, they tend to be equal mass binaries.
I have a question that I want to ask quickly. So I've always been curious how you get from sort of the 1 kilometer per second velocity dispersion of stars in molecular clouds to 80 kilometers per second for the oldest stars in the galaxy. And I think people thought that was mixing coming right out of the clouds. But now you're saying there's this sort of coherent stream. So do you think that the 80 kilometers per second preserves these streams and that it's a mixture of all the streams, or that there is some just total mixing at some point?
There is scattering. We must have
So
scattering.
how long, I mean, does anybody, it's been 5 days, I know,
Yeah.
but has anybody said anything about how long these kind of...
No.
coherent motions
To my
last?
knowledge, no. I think it's, so if you take the apogee data for Orion, I didn't talk about this, but this is work from Alvar Akar. You get, you do a friends of friends algorithm, and you find these tiny little groups of stars. And they have velocity dispersions below, well, the order of the error of the measurement, 0.25 kilometers per second. So you have like 10 stars completely frozen, flying through. And there's no interaction likely in any time soon. So these groups, by the way, this group in Princeton, it's a paper by Ho and collaborators, where they find an excess of pairs in the DR1 data. This is, well, there's all these pairs that they have moved together. And I think this is probably the tip of the iceberg of what's coming out of star formation.
And it's probably related to the fact that this is very weird phenomenon that the velocity dispersion of very young stars is actually smaller than, very small cores that are about to form stars is smaller than the velocity dispersion of the gas in which they sit, which makes no sense, okay?
Yeah.
But it's true, and I think is related to this. Phil, did you have a question?
Yeah, Joao, you showed a hint of what I'm going to ask about.
Okay.
I'm curious, with the precision of Gaia, will it be possible to discover where molecular clouds that are not visible now must have been? Because if you trace the positions of stars back to a point of convergence, you see that there must have been a place where the high density of stars required a high density of molecular gas to have been present then, even though it's not visible now.
Right. So this is what I was saying, and obviously that was not very clear. If you trace back SCOSAN, you find out that even this cluster, which was considered not to be part of SCOSAN, they go back, and you stop integrating what we think are the edges of the clusters. They go back to a volume of space, which is only 100 parsecs, which is about the size of Orion, Orion 1, Orion A, and Orion B. So yes, we can do that. We are able to do that for much more than just SCOSAN. We can do that for the local neighborhood perfectly, and even beyond that with further releases. So this is part of the excitement that the argument will be that we think we know where the cloud was that formed SCOSAN and I think 2602.
Do you think this could be applied to a big volume of the Milky Way, or will it just be confusion limited to just 200 parsecs?
You could. I have a plot to give you an idea of there. This is the same thing as before, except that now you're going to 500 parsecs. It's trimmed, and you can see immediately this is the R2. And you can see at the edges you have already the fingers of God showing up. So I showed you before the inner 200 parsecs. If you go to 400, Orion already looks stretched. And kiloparsecs about 10% error. Sorry, 10% error. So it'll be challenging, but surely for the local kiloparsec should be no problem. At some point.
So in DR3 or DR4?
Well, then will be much better. But I don't think you can do this for whatever volume you want. It depends on your precision, whatever you want. But it can be done, and it's fairly simple.
Yeah. So I had a question. Do you expect any dynamical structures in the solar neighborhood?
Any?
Kind of dynamical structures. So it's
yes.
sort of, not formed together as cluster, but kind of later came together.
So one thing that was very intriguing. I don't have them. You have to use a different. So if you use on the RKDE, which is you're doing here, just averaging stars. If you use a broad KDE, so you remove the noise, you get to be more sensitive. Turns out there's a lot of stuff where the sun is going through at the moment. It's the moving groups. The moving groups are a mystery to me at the moment, in the sense that I don't know if the moving groups are just around the sun and we just luckily find ourselves looking around happy because we get to see all this alma data with beautiful disks and all that. Or it's just that they're all over the place. We just don't have the resolution yet to figure out that this is actually an amazing network of tiny groups. So, as I told you before, from Orion, we find these groups of 10 stars with essentially no velocity dispersion, or velocity dispersion below 0.25 kilometers per second. These things will last. They will go, and maybe they populate the entire plane of the Milky Way. This is a bit too early to argue something like that. I think I put my head in enough guillotines, but this is, I think, very, very exciting. Yeah, it's a good point.
So this plot shows that you'd really like even better parallax, right?
Yeah.
For larger distance. So if you doubled the time baseline, you would then be able to go twice as far and 8 times the volume. So is there any talk of making it a 10-year mission instead of a 5?
There is, and it's wonderful. And the good news is yes. I think it looks all good.
The parallax. Does it? Sorry.
But you're going to find the three. You're going to be measured. So the mission is, maybe I shouldn't say something really stupid, but I think it's going to be exciting. I'm pretty sure it will be. I think it's been very successful. I'm going to have all these people now send me emails.
No one's watching. Okay.
No one is watching anyway. Yes, it'll be. I think it'll be exciting. And you can start measuring accelerations.
Maybe on that exciting note, we should thank you again before we get any more trouble.
Yeah.